Okay, so now we're going to talk about the energy landscape of reaction and how it decides, what K roughly looks like, what's favored versus products or reactants at equilibrium, so on and so forth. So I've drawn, three situations here. It's like, the Goldilocks and the three bears or whatever. One of them, the reactants are, too energetic, and the other one's just right, and the other one, the products are too energetic or whatever. But anyway, these are kind of the three situations, right? You can have reactants that go to lower energy products, you can have reactants that go to higher energy products, or about the same. Okay, so these are about even. And so equilibrium, here's the 2-second answer. Favors the low energy side. Low energy side, favored. Low energy side, favored. So products are favored over here, reactants are favored over here. Over here, it's about 50-50, they're about the same. Why would it favor one side over the other? So, this is like what every parent strives for, and then one of these situations, there's always a favorite. It happens. I assume, I'm an only child, so I didn't have these issues, but, I don't know. I feel like if I had a couple of kids, I would definitely like one more than the others, so I just project that on everybody. Anyway, now I'm going to explain the same thing a different way. So this is the kind of video where if something's not making sense, understand that I'm explaining something that you probably understand from a different explanation, but I'm just explaining it in a new perspective because we have all these new chemistry tools at our disposal. I mean, we're really rounding into some heavy stuff in the class, and we've gone through quite a bit. And so I can also talk about activation energies. So remember that at equilibrium, reaction rates equal out. Forward reaction, reverse reaction, go at the same rate. If I have different activation energies, I need different ratios of concentrations. A small activation energy will progress readily with a smaller concentration of reactants. This one will happen pretty easily. To get the reverse to happen, takes a lot of energy. It's not likely to happen. But as I increase my concentration of products, i.e. the favored side, it's going to start speeding that reaction up, and eventually the increase in products will overcome the need for a large activation energy to equal the rate, and then we've reached equilibrium. So activation energies and rates, you thought you were done with those? Maybe you thought you were done with these. By the way, which one of these is exothermic, which one's endothermic? It never ends. Now, I love asking those questions to a class. Camera is not quite as rewarding. I like to see the shocked look on your faces as I bring those terms back. Which one is a positive delta H? Which one is a negative delta H? So on and so forth. And I'm not even going to tell you, because whatever, you've got your book, you can look it up if you remember. Or maybe you just remember, but if not, you have your book, you can look it up. All right, so the next detail. So, activation energy argument for what it would take for the rates to equal out. And then there's also, well, what does that mean KEQ is going to look like? Well, KEQ is going to be larger than 1 here, but we'll start in the middle for that explanation. This one's going to be about 1 because you're going to have equal products and reactants. You put that in fraction form. Your denominator or your numerator and your denominator are about the same. 2 divided by 2, that's 1. Same number on top and bottom, you get about 1. There's a little wiggle room there for, stuff, but that's 1. So when we're not in that situation, we must either be larger than 1 or smaller than 1. That's just logic, right? So in this case, we're larger than 1 because we have more products. That means the numerator is larger because products go on top, reactants go on bottom. So the product is going to be much more favored. The numerator is going to be much larger. And so we're going to have a large number divided by a smaller number, which means we're going to get something greater than 1, like 10 divided by 3 or something like that. And then over here we get the opposite. Reactants are favored, large denominator, small numerator. So now it's like 3 divided by 10. And so when you see KEQ greater than 1, products are favored. If it's about 1, then they're about even. When it's less than 1, we say reactants are favored. And then that's what, it looks like in terms of energy landscape of what our reaction looks like. So again, remember our energies are y-axis, progress of reaction on the x-axis. So we start with reactants, we end with products. There's some change in energy, or maybe not. You got an activation energy in the middle to get the thing started. You got to overcome the bump. And maybe you end up uphill, maybe you end up overall downhill, so on and so forth. So you can use these diagrams to predict roughly what KEQ is going to look like. It's not going to be like, oh, I look at this and go, it's obviously a 97.3. No, but we know it's greater than 1. That's all we're looking for there. And that it favors products. Okay. And then, the activation energy stuff, that's a little highbrow, a little high level, but think about it. You can make sense of it. It's really drawing back to the fundamentals of chemical reaction rates. But that's okay. All right, so that'll do it for kind of introducing the equilibrium constant. Next, we're going to talk about some tricks you can do to manipulate equilibrium constants. Like if you do Hess's law stuff and you put reactions together, you can play around with equilibrium constants and get an equilibrium constant for the new reaction. Anyway, you'll see. We'll do a whole video on it.